Welcome everybody back to Math 480, which is algebraic, scientific, and statistical computing using SAGE. First, does anybody not have a copy of the syllabus? You would like a copy of the syllabus? Syllabus? Okay. Second, the first homework assignment is in my hands, so I'll hand it out. So just take a copy and hand it on to somebody else. We'll start this at the end of the the homework problems are supposed to be mostly very, very easy if you already know, say, Python and something about SAGE. And probably maybe a lot harder if you don't, but that will change. So the homework, I'm assigning it today, as it says right on the top of the homework. It's due on April 9th, which is 1 week from today. So what you'll do is you'll hand it in next Wednesday, and the second you hand it in, I'm going to take all of the handed in assignments, which will be sitting right here at the beginning of class. I'm going to randomly redistribute them to you. So what you're going to get is somebody else's claim that a certain Python program does something, or some code does something, or something like that. And you're going to look at that other person's code, and you're going to see whether or not you agree. And you're going to give them a grade. And then on Friday, 2 days later, everybody will hand in the graded version of somebody else's homework, and then the official grader, who is Robert Miller, who is not here but better be here. Oh, there he is. Okay, so he will look over everything that you graded and he will assign a grade. That will be the official grade. He can change anything you do in any way he wants. The main thing is, if you see somebody and they did something that just seems completely ridiculous to you, put a big X and say why you think that's completely wrong. And let's say also if somebody has a clever solution to a problem you looked at and you didn't come up with a nice solution, you can make that remark. And that'll just kind of inform Robert in how he grades. Okay? Any questions about that? Yes, Emily?
For things like using the SAGE command line and using
Yeah.
the SAGE notebook, should we print the output that we have, or can we just write an answer on a piece of paper?
Let me remember.
All
So
those
these are-
number twos and something.
Yeah, that one's kind of silly. With that particular problem, you can probably just say, I did it, trust me. Because there's not really much to be done there. Where I misspelled parentheses here, that's a typo. I do know how to spell parentheses. In 3, there you can literally, you can give what the correct parenthesization is. But yeah. So specifically on problem 2, just say I did it. Sign your name. I don't know. That was just like a kind of really easy problem to get you going. That's all it's meant to be. Nothing else. Okay? Obviously. Any other questions? If you have any questions about what's expected on the homework, just ask. Ask now, ask me an email, ask an IRC, whatever.
Where's the homework?
There should be one coming around. Where's the homework right now?
There's a bunch right here.
Excellent.
Okay, thank you.
Okay, cool. Here's the schedule for today. I'm going to try to make every day like this, where you know exactly what's going to happen. Question in the back?
No, I
Oh, you need homework.
Okay.
Here, make sure it goes back that way. Before I go on, since I just talked about grading, I don't claim anything about this being in order. We just talked about this. Maybe kind of just to continue that theme, looking at the syllabus, your homework is going to be 40% of your grade. There'll be a take-home midterm, which is 20%, and there'll be a final project, which is 40%. Notice the key thing, there are no in-class exams at all. There's no in-class final, there's no in-class midterm. So that's probably good from your point of view. The homework counts for a lot. I didn't explicitly say this, but I'll write it on the board right now. I will drop your 2 lowest homework grades. And I'll put that on the website. Sorry for not writing that. What this means, basically, one of your grades gets dropped because you messed up and did something wrong. The other one gets dropped because you decided not to do the assignment since you had to go traveling or something. Okay? So I'll never accept anything late, but I'll just drop the 2 lowest. It's just simpler that way. Of course, I encourage you to do all of the homework assignments. Any questions about the fact that you will be grading other students in the class homework each week? Since you probably haven't done that in other classes. If you're going if in a month you're going to say, hey, this is completely unfair, I should be paid, to grade another student's homework, then you should leave the class, because this happened to me once last year when I taught Math 480, and it was very odd that a student was demanding to be paid to grade another student's homework. Because really, I mean, it's not about trying to minimize my work or something, it's about you getting the experience of understanding what's needed to write up a solution that other people can understand. Because that's really the goal. I mean, now if you have to read other people's solutions, you'll start thinking, okay, wait, what do I need to do in order to write something that's comprehensible to other students in the class? So that's the end goal. The final project, so that's 40% of your grade, and it's going to be written in some form. And that's something that you should feel some worry about or anxiety about, because it's not so precise as a typical kind of math exam or something. I mean, at the end of the day, the grading of the final project is it's sort of arbitrary and up to me. So I'm going to try to give you as much feedback about how I grade a final project before the final projects are due. For example, there's a date which is listed back, yes, Wednesday, May 21st, a rough draft of your project will be due. And on that day when you hand it in, I will give you, not on that day, but after that, I will grade it. It'll be a rough draft, I'll grade it, and I'll hand you back the thing graded. The grade won't count at all towards your grade, but it will give you an indication of how I grade a project. So you'll have a sense of whether you're doing the right thing or not, and what sort of things you need to change in order to get a very good grade on your final project. So the main point of the rough draft that's due on May 21st is just to help you calibrate what you're supposed to do to get an A on the final project, okay? So you don't feel some anxiety about what it means to do a good final project. Also, I think you should start thinking about what you might do a final project on as soon as possible. Right now even, just think, what could I possibly do something on that's maybe related to computation? So just start thinking along those lines. You could pick up something at any point and then go for it. So I mean, probably a nebulous thing to you, but an example of a final project that Allison did in a class I taught 2 quarters ago, there's an algorithm for finding a really good basis for a lattice called Triple L, the LLL algorithm, which has had a huge impact on a whole bunch of aspects of cryptography and computer algebra and so on. And she implemented the algorithm and then drew, she did something where you take a matrix and you run the algorithm on the matrix, and then she drew a picture of the matrix as the algorithm runs. So you see kind of an animation as the matrix goes from the input matrix to the answer matrix. And so you see this neat sequence of pictures. So in her paper, she wrote up something about what she did, and then also included the code that draws this sequence of pictures. So that was a nice project, right? Fun, you learned a lot. It was really surprisingly hard, but you certainly learned a lot more about Triple L than you would have just by hearing about it in class, wouldn't you say? Okay, great. So that's an example of the sort of thing that might be a project. Since I seem to be going in reverse, so that's done, this is done.
You did 3.
Oh yeah, Robert is now introduced. That's Robert Miller. He's the official Sage TA and TA for this course. So he's hired by UW to help out with Sage. Robert Miller. And his contact information is on the course website now. Okay, work opportunities. So the specific things I wanted to mention right now. One, there's something called the Google Summer of Code. I don't know if anybody's ever heard of it, but it's an internship that Google funds, and they give you, you have to be a student. You have to be a student to do it, and they fund something like, I don't know, they give you something like $4,500 to work on some open source project all summer. The application deadline was Monday, but then they moved it forward, so it's actually next Monday. So if this is something that might be of interest to you, so you're getting paid by Google to work on some open source project, for example, the Sage Notebook right here, this thing that you're looking at, this JavaScript, Python, web-based application, that is something you might be able to get funded by Google to work on all summer. So if you're very interested in, say, doing something like that, contact me. So that's a possibility. Is E here? Chris DeVona wrote back to me a few minutes ago, saying he's looking at our email. So that's related. Other work opportunities. So this is actually a clean-cut thing somebody could do. So there's something called Microsoft Virtual PC. Has anyone here ever heard of it? Raise your hand if you've heard of Virtual PC. Okay, so it's a program that lets you run Windows under Windows, basically, or Linux under Windows, or lets you run some x86 operating system under Windows. And Microsoft would very much like it to be the case that there is a virtual PC version of Sage. That is an install of Linux into Virtual PC, which you can then run under Windows. Right now we have a VMware version of Sage, but we don't have a Virtual PC version of Sage. Microsoft has given me money to hire a UW student to make a Virtual PC version of Sage. So if anybody's interested in being paid through UW by Microsoft to create such a thing, please contact me. So it would be very nice if somebody could volunteer to do that. Basically, all the skills you need are to use Virtual PC and to know how to install Linux into it. And there's not much more than that. So it could be a project of interest to somebody in here. And you'd get paid on an hourly wage. Okay, so that's some job opportunities. Okay, so there we are. So now I'm going to finish the demo I started yesterday, and then I'm going to talk about lists and tuples, which are two things in Python. So here we go. So first, you'll remember last time, I talked about an example where you define a function that tells you whether or not an integer is a power of 2. And I defined that function in Python, and then I tried it out. And that is a bug, by the way. It's synchronization stuff. It seems like a new bug. Shouldn't be there. In any case, that function is slow. It takes a long time. Write exactly the same function, but in Python, which means putting %Python here and having the option of explicitly declaring data types. Then you see that the same function is a little bit faster. So there we are, trying the same function. It's, well, it takes 0.03 seconds to do that calculation instead of 1.74 seconds, or 1.85 this time. So it's about 60 times difference in speed. The point of this example is that Python can be really slow for certain types of calculations. You have to watch out. And this sort of thing is something where C, which is really what Python gives you, if you click on this link, you'll find a C file, which this gets turned into. It gets compiled to C and then loaded. And it's quite fast at this sort of thing. Whereas Python is not so fast at this sort of thing. So Python, the language that Sage uses, though it's really fast for you to write code, it has many other nice benefits. For example, it's easy for people to read the code you write. It's not the fastest language out there. And C is really, really fast in comparison to Python for certain things, as far as the actual speed goes. So you have to be aware of that. But don't worry, because at least it is possible to write fast code in Sage. By the way, I'll click on this link right here. What this does is it gives us the code that we just compiled. But if we click on this, we see code that gets generated from the code that we compiled. I'll go into detail more, I think, later next week. I have a whole day that's devoted to Python next week. So I won't say anything more now. But basically, Python is a way of compiling Python so that you get code that is very fast, as you can see. By the way, you could do this example. I don't actually know what's going to happen. But we can take it and not explicitly say what the data type is. And then we're going to get much less of a speed up. In fact, let's see what happens. Wow, that's weird. That was pretty good. Huh. So it's 30 times faster, and I didn't change anything. Cool. That's impressive. One of the Python developers ran some subset of the Python standard benchmarking suite, and it turned out Python ran, I think, the overall benchmark roughly 30% faster than pure Python. So in some generic sense, if you take a Python program and then just put %Python above it, in other words, compile it, you'll get a speed up. If you don't declare any data types or do anything special, you'll tend to get a speed up of about 30% for what it's worth. Okay, moving on. So I'm going to tell you about a few other things. Here's a relatively new feature in Sage called Interact. Has anybody here ever heard of Mathematica's manipulate command? It's a new feature in Mathematica 6. So you have. And it's pretty neat, right? If you've tried it. There's a lot of cool things you can do. It's kind of like plot, except instead of getting a plot once and for all, it gives you some controls that allow you to manipulate the ranges of inputs and then see what the output is. And Sage now has a very similar functionality called Interact, which what you do is you define a Python function, and all you do is you put this right above it, at interact, and it makes the function interactive in that you have some widgets that allow you to change the inputs and see what output you get. So what I've done here is I've defined a sort of ridiculous function. It takes a number n as input and some other thing f as input, and it prints out the factorization of the number, and it shows a plot of the function. They're kind of two unrelated things. So if I just define this function and then run it, I'd have to type in specific values, and then I would see a number that's factored and a plot. But with Interact, it's a little nicer because you get to type in things. So here, I press Shift-Enter to evaluate the cell. It automatically created an input field for n, an input field for f, factored n, and drew a plot of f. Now I can change the value of n to something else, like that. And then when I... Wow, why is that? So you can see that it factors... God, that's weird. Why does that print there? Well, anyways, as I enter a number, it changes the output. So also with the plot. So if I don't know why this is here. It wasn't here when I was preparing this in my office, and I really annoyed by that. But I will say nothing further about it. So you can see if I change the input function, then it nicely draws another function there. So it's kind of a nice thing because you can vary the ranges of parameters and see what happens. Here's another example right here. Here what you do is let me zoom out a little. Here what you do is you click on one of these buttons, and it gives you the corresponding parametric surface. The buttons are Boy's surface, cross-cap, double heart, and so on. You can choose whether you want to see a ray-traced image or not, whether you want a frame around the image, and what level of opacity you want in the image. And to set this up, I did something very similar to what I did above. The code is longer, but let me click, show it to you. It's hidden here. So I defined a function. I just called it underscore because I couldn't think of a good name for it. It took as input something that allows you to select one of the plots and whether or not you want to ray trace and so on, how much opacity you want the image to have. And then based on what your input is, it draws one of the parametric plots. So let me show you this in real time. So let's just choose something, let's say the cross cap. So the real projective plane. And there it is. And it's annoying because you can't drag it around or anything, unless you turn off ray tracing. And then it draws it using some cool Java program. So there it is, that's a 3D image. It's kind of hard to see inside. Probably kind of hard to see at all. But right here, it sort of crosses over inside itself. Fortunately, I can zoom in a little more. One thing I can do is turn on transparency, and you can see through it somewhat, which is kind of fun. So I'll make it more transparent. Now you can see inside a little bit. Probably kind of hard to see, but you can sort of see inside. There's other images are a little easier to look at. So let's try, say the bow tie. That one looks pretty neat. So there's a bow tie image. You can see it's kind of transparent. You can rotate it around and zoom in and so on.
You should have brought the 3D goggles.
Yes, if you have 3D glasses, it's kind of fun because you can do style stereographic red-blue. And then you can see it with 3D glasses. And if you're good at crossing your eyes, there's also cross-eyed view. So, I don't know if you can see that at all. Get out of your way, maybe you can. If you cross your eyes a little, don't get dizzy or anyone just fall into their chairs. So this is just illustrating this interact command. I'll probably use it a lot for demos of certain things in class. We'll see. Okay. All right, moving on. So now I'm going to show you just a couple of examples of calculations that are related to algebraic computation, scientific computation, and statistical computation. Just a couple. First, let me zoom in so that you can see. So first, here's an example. I construct a symmetric group on 4 symbols. So this is a group of order 4 factorial. It's all permutations of 4 things. So some of you have taken an algebra class and you know about groups and rings and fields and so on, and some of you haven't. Actually, how many people here have taken some algebra and know what groups, rings, and fields are? Excellent, excellent. But don't worry if you don't. A group is just a set with a way of basically multiplying together elements in the set to get another element in the set that satisfies certain conditions. So, for example, if you take 5 things and consider all possible ways of permuting them, then that is a group, an example of a group. Here's a non-trivial calculation computing the derived series. Wow, that is annoying. Okay, so computing the derived series of a group. So we have a group here, and then the derived series is a certain collection of subgroups of the group that you get via a certain operation, and it ends up at the trivial group. So here we see how to compute that. Here's an example of computing the Cayley graph of a group and printing it out, and there it is. And this is a graph with a vertex at each group element. So that's an example of some groups. Here's an example of a ring, the ring of integers. A ring is it's a set where you can multiply things together and you can also add them. And then again, there's some conditions that are supposed to be satisfied. The integers, or the real numbers, or the rational numbers. These are all examples of rings. Also, a popular ring that people work with every day is the ring of integers modulo 12, which is sitting right there on the wall, the clock. For example, if you can do arithmetic there. If you let R be the ring of integers modulo 12, and then take, say, R of 2, which is right now, and then add to it, I don't know, 17 hours, it'll be 7 a.m. or p.m. I don't know which. So what happens when we do the arithmetic is it adds 2 and 17 to get 19, but then it reduces it modulo 12. And 19 modulo 12, if you divide and take the remainder, is 7. So this is a ring where the arithmetic is addition mod 12, and the elements of the ring, which you can get by doing r.list, are right there, 0 through 11. Here's another example of a ring, the polynomial ring in 2 variables. So if you take all polynomials in x and y, then you can add them together and you again get a polynomial x and y. You can multiply them together and you get a polynomial x and y. And that forms a ring, some like collection of mathematical elements that come up in mathematics that are closed under multiplication and addition. Some other rings I mentioned already. Here's a ring GF9A. This is a finite field, which is something that is really important mainly in coding theory and cryptography. So a finite field is a special type of ring where not only can you multiply things, but you can divide them, and in addition, it's finite, so there's only finitely many elements in there. And this is one non-trivial example of such a thing. Here's an example of using the interact command. What you give is, you type in a number right here, and what it will do is construct So the number has to be a prime power. That's a theorem. If it isn't a prime power, you don't get anything. But what you do is you type in a number and it will construct the unique up to isomorphism finite field with that order. And then it will list all of the elements, which is kind of boring because I mean, it would be easy to do that anyways in this. But maybe one interesting thing is it gives you a polynomial that defines the finite field. So I'll just do an example where I make this bigger, and I get all the elements in a finite field of order 81. And if you're a little bit more industrious, you can make a multiplication table or something like that. So that's just an example. Here's a fun example of an implementation of choosing parameters and then displaying the Diffie-Hellman Key Exchange, which is something that comes up in public key cryptography. The Diffie-Hellman Key Exchange was the first ever published example of a way of, in kind of plain view of an adversary agreeing on a shared private key, which you could then later use for communication. Until the paper by Diffie and Hellman was published, if you wanted to agree on some private key, you basically had to send something through the mail or send somebody with a briefcase handcuffed to their wrist or something in order to exchange the private key. Or you had to come up with some complicated system of coming up with new private keys based on some keys you had already. So this Diffie-Hellman thing was an amazing accomplishment. And here's an example of just playing around with it. It's kind of small, so let me zoom in even more. Here we are. So this illustrates how the Diffie-Hellman Key Exchange works for a given choice of a prime. So I won't go through this, that's something to do later. But the fun thing is you can if you drag the slider, it goes through and does a complete example of the Diffie-Hellman Key Exchange, but for a given size. Very quickly, so the way it works is the two people that want to agree on a secret key choose a prime p and a base, and anyone can watch them choose the prime and the base. And they just agree on it in public. Then completely secretly, Alice, hiding with her little computer, chooses a random number and raises G, which in this case was 2, to that random number, and then just sends that power out. So the power in this case was the number right there. Likewise, Bob does the same thing. Secretly, without anybody looking, he chooses a random b and then sends G to the power of b modulo p out. And anybody can watch that get sent. Then Alice computes what Bob sent to the power of a, reduces the result modulo p, and gets a number. And likewise, Bob does the same thing and gets a number. And the two numbers agree. And the really, really bizarre thing is that knowing everything that gets sent back and forth, it seems to be extraordinarily difficult to figure out what this number is that Alice and Bob agree on if you don't know either A or B. So it was interesting, when the paper first appeared by Diffie and Hellman in Mathematical Reviews, the reviewer said, the reviewer is not convinced that this thing works. But it turns out that it does work, and it's used all the time by people. And in Sage, you can really generate quite big examples of this pretty quickly. So just as I'm doing this in real time, it's running through the entire protocol. Wow, it suddenly got slow at that size. How did that get slow? 212 it did instantly. That's disturbing. Go away. Or not? Still doing that previous example. So I'll illustrate something about the notebook. If you can't interrupt what's going on, oh, I interrupted it. Good. Okay, so 88. I wonder why it takes a long time sometimes. It's weird. Because there's a 284-bit example. I mean, these are big numbers, so I don't know why sometimes it takes a long time. Okay, on to some other examples. Here's an example from linear algebra. I already showed you some like this last time, but I make up a random matrix and compute its characteristic quantity. It's pretty straightforward. Two things to note about this. Well, one thing to note about this is by typing show of an object, I get a nice typeset version. If I didn't type show anywhere up there, I'd see essentially the same output, but it would look much uglier. It just kind of look like one-dimensional ASCII output. So that's a little bit of a... Here's an example to kind of push the limits a little further. So I just made up a random 500 by 500 matrix, and now I'm going to compute its determinant. So there it is. It's a pretty big determinant, as you can see. Goes on for a while. And it took a little over 2 seconds to compute that. So if you think about it, it's probably not doing expansion by cofactors. It's not looking at the first one and then computing the determinant of the submatrix and so on, because the complexity of that would be about 500 factorial operations, which would take a long, 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 long time. So it's doing something much better. And I'll talk about what it does, which Hamad recently explained to me. Not now, but later on in the course. Okay, moving on to scientific computing. Yes, you can do arithmetic with floating point numbers in Sage. So here's an example of adding together two. Maybe be more impressive if I had that or something. Or you could put pi, but that's not so. See, so you could do arithmetic with floating point numbers. Here's an example where, so that's another one of these interactive examples. So it turns out in Sage there are really 5 different ways to work with floating point numbers. There's, I guess in a sense, there's 3 really distinct ways. You can work with double precision numbers. It's kind of like in MATLAB, say, where you have single precision, double precision. You have a couple of different things. So in Sage you have double precision numbers, multi-precision numbers, where you specify that all the numbers you're going to work with have, say, 200 bits of precision. And with each of these, you can also specify a rounding mode. So when you do arithmetic operations and it rounds, it can round down, up, towards 0, that sort of thing. There's also a very, very good implementation of interval arithmetic, where again you can specify the precision. And it's both complex and real interval arithmetic. So just to give you a little bit of an example of that, what you do here is you choose, say, the multi-precision real field, and then you say how many bits of precision you want. And what it's doing is it's coercing pi into that field. So it's computing pi with 100 bits of precision, and then printing out the result. And also pi squared. You could try this with more bits of precision, like, say, 1,000. You can see it's pretty quick at doing this. So there's pi to 1,000, or actually to 10,000 bits of precision. And you can do arithmetic with pi to high precision and so on. One thing that Sage does very, very little of at present is, I guess, well thought out, clever linear algebra with numbers that have large precision. With double precision, linear algebra is extremely good. But if you want to do linear algebra and have all your numbers have 500 bits of precision, Sage just uses fairly generic algorithms. So it'll, if you ask to solve ax equal to b, it'll find the reduced row echelon form in the most obvious way possible and possibly give you the answer. So it's not very clever there. And there's definitely potentially interesting research to be done as far as arbitrary precision linear algebra goes. So getting past pi. Here's an example of numerical linear algebra. So I just made a 3 by 3 matrix, and I used the random matrix command, which makes a random matrix. And it's a pretty flexible command. What you give in the first position is the ring or field where you want the entries of the matrix to lie. And in the second position, you give the size of the matrix, the number of rows and columns. So here, since it's square, I could just leave off the number of columns and just give the number of rows. The default, if you only specify one thing right there, is that it's square. And there's the matrix that I get. By the way, if you only remember, let's say you wanted a random matrix and you couldn't think of anything else to do. So the first thing you might try is to type RAN and then hit the tab key. And what that will do is give you everything that starts with RAN in Sage. And you'll notice that there's something called random matrix right here. If you then select it, then you think, geez, I have no clue how this works. If you hit open parentheses and hit tab, it'll show you how the thing works. And you can see the input that is given. It's a ring with a number of rows and a number of columns. And then there's an example here. You can also make the matrix sparse or dense or whatever else. So that's all you have to remember. Okay, so now let's compute a lower upper factorization. So there you are. So this computes an LU factorization of that matrix whose entries are in a real double field. And that's all you do, just type matrix.lu. And if you forgot that that's what you're supposed to do, you could take your matrix. It's kind of like context-sensitive help. You take the matrix, put a dot, and then hit the tab key. And it shows you all the things that you can do with the matrix.
What if it doesn't have an LU factorization?
I don't know.
Every matrix has an LU factor.
Give me an example. Let's find out. Well, no, this is a PLU.
Oh, okay.
Look, see.
You wrote LU then.
Well, I don't know why. I didn't write this code. Josh
But you might
can't read it.
You might have.
Yeah, it always.
before you think.
Maybe it should be renamed PLU.
PLU should be-
I don't know. Maybe this is sort of a standard convention in numerical software. I don't know. I didn't write this, so I can ask why Josh called the thing that returns PLU LU. And I think it probably just exactly follows what GSL and NumPy and a lot of libraries do. So maybe people always compute a PLU. Just to kind of see if this thing works when the input is big, let's make up a random 1,000 by 1,000 matrix that has 1,000,000 entries, and then try to compute an LU decomposition, or a PLU decomposition, sorry. Let's see, oh wait, it's already done, 1.6 seconds. So you could do these decompositions pretty quickly. All right, next example, symbolic integration. So you can type in a function and then integrate it and get an answer. And by the way, just like before, if you type show, you can get the answer in a way that is typeset and looks a little prettier. By the way, the typesetting here is pretty neat. It's not just an image there. It scales nicely, and you can select individual characters out of there. Let's see. Oh, and you can see the LaTeX representation. So see, each character is an actual character. Look, see, I'm able to select them. And if I double click, I see the LaTeX. So if you have some expression and you want to paste it into a paper you're writing, and you use LaTeX or something that can parse LaTeX, you can double click and then paste it like this. You can also give in anything in Sage. Here's a really scary looking interval in Sage at least. So that looks pretty painful. Imagine if you had to type that into a paper. Fortunately, you can say LaTeX of it, and it just gives you the LaTeX that if you paste it in, it'll look good. And
How does that look pretty?
how does that look? It looks like this. So, yeah, it's readable. Here's another example of an integral. So if you take kind of any random integral from, say, a second semester calculus course or third quarter calculus course or whatever, and type it into here, it's very likely to be able to do your integral. Okay, and now that's a little out of order. Okay, now I'm going to show you the very end of this presentation, just a little tiny bit of statistics in Sage. So there are two completely distinct packages for doing statistics in Sage. One is called scipy.stats, and it's a Python library that's mainly produced by a company called Nthought in Texas, which I recently spent a week at for Sage Days 8. Here's the Nthought webpage. They're a real live company, and I think they're doing pretty well based on the sizes of their houses and cars and stuff. Seem to be, and their headquarters. I mean, it's a beautiful office building right in downtown Austin, with a lot of space and a lot of Herman Miller chairs and all that. So you can see they're hiring. So if you get really into scientific computing using Python, you might work there. Who knows? They have a lot of employees. And they're an open source company. Essentially everything they do is BSD licensed. So So they're very, very supportive of open source. In particular, they are very supportive of this SciPy stats thing. They're kind of the home of SciPy and NumPy, which is related to SciPy. So anyways, SciPy.stats, you can import it, and then if you do SciPy.stats.tab, you'll get a sense of the sorts of things it does. And you can see there's just a big list of statistical functions. You just keep scrolling down. So there's quite a lot of different things it can do, as you can see. So it's very powerful. Apparently when I was there, they told me they had a recent conference in which people from the R project and from various statistical software projects, a bunch of closed source projects, all got together and had a lot of discussions. And it was interesting. I guess they said that the R people think that SciPy stats doesn't do very much, but the SciPy stats people think that it does a lot, and a lot more than the R people give them credit for. Apparently, well, I don't want to say much more than that, because there'll be time for this later. But here's an example of something SciPy stats can do. You can compute the standard deviation and mean of some numbers. Okay, that's not very hard, but just an example. So just a little tiny thing. You can also do, say, a t-test. So there's an example of the output of doing a t-test for this particular data, assuming that population mean. Okay, so that's SciPy stats. There's a lot of stuff in there. It's growing. I think they're going to put a lot of work into making it better, et cetera, et cetera. So that's one of the two ways in which you can use statistical functionality in Sage. And by the way, I've used statistical functionality in Sage, even from a number theorist's point of view, as extremely important. Because I find personally in my number theory research, often what happens is I compute a whole bunch of data, and then I need to try to make sense of it. And statistics is really, really useful for trying to make sense of a whole bunch of data. So frequently, in fact, in the research I do, I end up needing statistical functionality in order to understand all these numbers that come out of some very abstract number theoretic calculation. And in fact, there's a nice paper in the Bulletins of the AMS, which is one of the big mathematics journals that I published a couple of months ago with Barry Mazur and Mark Watkins and this undergraduate. And it's about a huge, huge data set of elliptic curves and some really kind of statistical analysis of the data. Some surprising conjectures. Okay, the other way in which to do statistical computing in Sage is R, which is one of kind of the main, probably the biggest package for doing statistics out there, is part of Sage. So every time anyone gets a copy of Sage, R is included in there. And all the functionality of R can be used through Sage. So if you take a class and they use, has anyone here ever taken a class where R was used in the course? So a couple of, 4 or 5 of you already. So you'll be way ahead of the game when we come to the statistics part of this class. Because a lot of what we'll talk about is using R through Sage. So here's a really, really simple example of using R in Sage. Compute the mean and standard deviation of the same data that I mentioned before. But you can, there's a way to turn any command that you would type into R into a command that you type here. And if you look at the RPy website, R being this interface between Python and R, it explains how to turn R commands into RPy commands. Something that hasn't been done is, as far as I know, nobody's written a nice, kind of very Pythonic statistics package that does all of the calculations behind the scenes using R. And we'll wait and see if that happens. But there is one guy in I think Austria named Harold Schilly who's been working pretty hard on making it a lot easier to use R through Sage. And we'll see what comes of that. All right, so that is the end of yesterday's lecture, or Monday's lecture. And now, today's lecture. But let's see, how are we doing on time? So there's 6 minutes left. So I will pause for about 1 minute and see if you have any questions, and then I'll start on this, and then on Friday I will finish it. So any questions or comments before I continue? General concerns, questions, anything about Sage? Ask me anything. By the way, you should install Sage on your computer. But if you find that to be impossible, you can also go to this website right here. And it's sagenv.org. You can connect to it from anywhere. And it might be a good idea to go here and sign up for an account anyways. But the nice thing about this is you can use Sage from just any computer lab anywhere, or anywhere with a web browser. What you do is you click here where it says sign up for a new Sage Notebook account. And once you click there, you'll get a little screen where you can choose a login name and a password. And then you choose it, and then you can log in, as I'm about to do. And you'll get a list of your current worksheets. And you can say click on one. So I was wondering about some compound interest thing when I was driving in a car the other day. So I pulled up my cell phone and went to this web page and then typed in, not all of this, but I typed in this. No. So, but it was nice that I could, play around right there on my cell phone and do that calculation. So there you are. And by the way, one fun thing about this computer, I guess it's hard. This is a very powerful computer that this notebook runs on. So it has 64 gigabytes of RAM, though individual processes are limited. So that's that. So this may be useful for you. And you can also publish worksheets. So that's that. Okay, so on to the data type stuff. Close some of these other things.
I have a question.
Oh, yes.
If I was looking for some function that will do something for me,
Yes.
And I didn't know exactly what it's trying to do, is there a way I can do browse?
Yeah, there's a couple of things you can do. It's a great question. So let's go back to the end of yesterday, so this gets saved. So one thing you can do is right here there's a search command which you can run. And if you don't remember what it is, type the first few letters of the word search. And there's actually a couple of things, but the key thing you want to use is search doc. And then give me an example. Something you might want to do.
Inverting the matrix.
Okay. For that, you'd want to make a matrix, then type matrix dot, and then see what appears. But let's try just searching for the word invert. We're going to see we're going to see all instances of, or every page in the entire Sage reference manual that includes the word invert. So you will see, in fact, there is some stuff involving matrices here, which you would find useful. So let me try, say, clicking on matrix 2. So when you click there, what you get is a section of the Sage reference manual. And now if I search using Firefox, in that page, I should hopefully, this is kind of weird. I guess
I think it's Firefox.
this page is huge. So I think Firefox is still trying to render the page, which is really annoying. I will do a trick. Wow, poor Firefox. Okay, I'm also very impatient, so. The issue here is that each reference manual page comes up as a Sage worksheet itself when you do the search. And this is a massive, massive page. I mean, it's thousands and thousands of lines long. So it's just a huge, huge worksheet, and it's taking Firefox a long time to render it. Or something's funny with rendering it. I guess it's some bug in Firefox's rendering, as you can see. Maybe if I resize, it fixes that. So somewhere in there it says invert. Oops, sorry, now I'm looking at the wrong page, which is part of the problem. So that's one of the two ways. Let me show you the other way, which is a little safer. Okay, so the other way is to just look at the reference manual for Sage and then look in the index, which is really, really good. So I need to get a new tab. All right, Firefox is just not working. So if you go to the reference manual, which is in the Sage documentation, then here it is. And there's a lot of different chapters. For example, there's a chapter on matrices somewhere. Yeah, matrices and spaces of matrices. So in here, presumably you can find things about inverting matrices. Also, there's an index, which is really, really big. So here's the index, and you can just click on a letter, and then it'll give you every modular command or whatever that involves that letter. And you can also just do a full text search. So if I search for, say, inverse, I get something here, which is pretty specialized. This one looks useful. The inverse in matrix. And there we are. So this is the relevant section that tells you about inverting the matrix. So one of the best ways, if you just kind of have no idea where to look, is to look in the reference manual and just look at the back. And you can download the entire reference manual, which is about 3,000 pages, in PDF format right here, or just as an HTML document. Wow, it's going to just pop up right there. Okay, so there's the reference manual. There it is. So I could do a search for inverse, and then it's kind of big, so but inverse. More than 100 matches. Invert a two, and you see lots of examples. And kind of flip through them. Formal inverse of the factors in a factorization. Really, the best thing though is to create a matrix, say .invert, and then put question mark after it. Okay, so I will start fresh at the beginning next time with a discussion of lists and tuples, dictionaries, and other data structures. Okay? And also I have office hours for the next hour upstairs in 314. So if you want to talk to me, just go up one floor to the back over there to the Sage Lab, and then I have office hours. Yes?
Oh, that when I tried to